Thanks, Eli. Good morning, everyone. Glad to be here. Again, my name is Greg Nowacki. I'm with the U.S. Forest Service, located out of Milwaukee, Wisconsin. I'm affiliated with the Eastern Regional Office there. I'm the regional ecologist, acting soil program leader at this time, and de facto fire ecologist, so person who wears many hats. Glad to be here today. I'll be covering our ecological mapping and classification that takes place with the U.S. Forest Service spanning the eastern United States. I'll try to focus in on Minnesota as we go through the hierarchy today, highlighting some of the things that occur here in your fine state. So, presentation objectives. First of all, I want to provide an introduction to the National Hierarchical Framework of Ecological Units and its application across the East. I'd like to spatially step through the top 5 levels of the hierarchy itself, placing Minnesota's ecosystems into this broader ecological context. And lastly, discuss the uses of ecological units in both land management and research. So, what is the National Hierarchical Framework of Ecological Units? Well, simply it's the delineation of ecosystems at multiple scales within a nested hierarchy, again, to meet land management and research objectives. At the bottom level, generically, we refer to these as land units. They're small in size, tens of acres, hundreds of acres. And as you can imagine, because of their small size, there are many of them. Stepping up to landscapes, we're dealing with ecological units that are thousands of acres. And of course, there's fewer of those as you step up the hierarchy. Next, subregionals, delineations. These are hundreds of thousands of acres, up to about 1 million. And lastly, at the tippy top of our hierarchy, we have what we generically refer to as ecoregions. These are millions of acres or millions of square miles in size, and consequently, there are few of them. The U.S. Forest Service employs what we call a top-down, bottom-up approach. So we take these ecoregional units and we break them down into smaller units down to basically the landscape scale. Concurrent with that, we have experts out in the field, soil scientists and ecologists, that delineate land units. We refer to those as land type and land type phase units, and they aggregate those upwards. And somewhere in the middle, they meet. And indeed, that is the case here in Minnesota. We worked with people from the Superior National Forest and the CHIP, and also with DNR, John Almendinger and Dan Hansen, to employ this approach. So it does work, and it's the best of both worlds. We're bringing information down from the top, integrating information, and we are also simultaneously bringing it upwards from the bottom. Okay, employing the hierarchy, it falls within our terrestrial ecological unit inventory, as we call it, U.S. Forest Service. What are we doing? We're assigning ecological addresses to our lands. It provides the spatial context for understanding ecological and hydrological processes, disturbance regimes, vegetation and habitat patterns, understanding successional trajectories, and site productivity. Great for monitoring, developing experimental designs, and the extrapolation of models and management practices. We are characterizing the landscape here, and this is really a neat classification for use in land management planning and the execution of field projects therein. It's a fine template for ecosystem restoration, forming the baseline or reference conditions that we want to shoot for when employing that. And in the U.S. Forest Service, we have kind of a paramilitary organization, which many of you are familiar with. And this particular hierarchy allows for upwards reporting within that hierarchy. So ecosystems, what are they? They're places where biological and physical factors interact. And we're dealing with 3-dimensional terrestrial space, the atmosphere, the biosphere, the lithosphere. This is probably one of my most important slides right here. Form follows function, pattern reflects process. With ecological mapping and classification, we're putting lines around forms, around patterns. But what's important is what's occurring on the right-hand side here, understanding those ecological processes and how these ecosystems function. One of my favorite quotes, and I'm getting right now goosebumps with this one. This is from Norm Christensen, and this really captures the essence of what we call eco-mapping. Ecosystems are not defined so much by the objects they contain as by the processes that regulate them. So again, we're putting lines around objects, but what we really want to capture is those driving processes beneath those objects. So we all know that ecosystems are very complex and they're influenced by many different environmental factors, right? There's climate, topography, geology, hydrology, fauna and flora, soils and disturbance. It's pretty vexing, pretty intimidating when you're thinking that you're going to delineate ecosystems when you have all these balls up in the air. But that's the strengths of the hierarchy here, because we can dial in those principal environmental factors at the appropriate level, make it a bit more simple anyway to delineate ecosystems. And once you go through the hierarchy, going the top-down route, you can basically check marks along the way. You have incorporated this environmental factor, check mark, and you can go down to the next set. So it facilitates, it makes this process a bit more easy. So ecoregions, we have 3 levels within our hierarchy that fall into that: domains, divisions, and provinces. We dial into things such as macroclimate at this time and gross physiography. We oftentimes use vegetation at the biome level or forest region level as a surrogate for climate. Next down, we have subregions represented by sections and subsections. Now we're starting to get into subcontinental climate regimes, mesoclimate, if you will, starting to look at broader landforms, collections of those, always dialing in vegetation along the way. And geology becomes very important, both bedrock geology and surficial geology. The latter we'll concentrate on with a few slides, how important that is in the upper Great Lakes states and glaciation. Landscapes represented by 1 unit, land type associations. Here we're looking at repetitive patterns, repeats of landforms, for instance, on the land. It bodes well with the Katina thought pattern of soils, where you have a series of soil types from valley to ridgetop that repeats itself. So it's very much akin to that concept that we see in soil science. And lastly, land units. We have 2 ecological units falling in this realm. Those are land type and land type phases. Here we're looking at local climates. Physiography becomes very important in regards to aspect and slope, integrating that into our ecological units, looking at fine level vegetation patterns, communities, forest stands. And we're very much interested in soil properties, such as soil pH, soil texture, soil drainage. As most of you are aware, NRCS, they have a soil taxonomic system that they use. And there's a lot of good information that we mine from the soil series in their maps. But one thing to point out is that vegetation follows soil properties and not necessarily taxonomies. So that's why we really lean heavily on soil properties for ecological mapping and classification rather than their taxonomy per se. And again, for this presentation here, we're going to be concentrating on those 5 top levels. John Almendinger, who is coming up next, will help fill out the bottom 3 rungs with his presentation. Okay, domains. First of all, notice the code that's being used here, hundreds. So the first number in that column refers to a domain. We have 3, at least proposed here in the eastern United States. Historically, there was only 2. We had 200s represented by the humid temperate, and then a little bit of humid tropical down in South Florida. I was always perplexed why the humid temperate usurped this entire area of eastern United States. As a young lad driving up with my father up to the Boundary Waters. I'm from central Wisconsin. I just remember rounding the horn by Duluth, you know, going up in the plateau, and then all at once, bang, you're just in a totally different world. And very boreal, conifer dominated, very cold territory, as most of you are aware. And it was a bit perplexing why in the past we put that in the 200s in the humid temperate. I want to change that, and this is the first step. What you're seeing here is actually the next, it's an updated version of our hierarchy being presented for the first time. Hasn't been anointed yet by the Washington office, mind you, but hopefully these things will hold true. So, brought in the boreal, what I'm calling the boreal domain into northern Minnesota. And one additional thing I want to point out is historically our older maps always truncated themselves at the international boundary. Drives me wild. Can't stand it as an ecologist. So working with our GIS folks at the regional office, we were able to bring in ecological units from Manitoba, Ontario, Quebec, and New Brunswick. Bring those elements in, those units in, and then we can basically delineate our ecosystems in their entirety rather than having this artificial truncation at the international boundary. Focusing in on this boreal domain that I refer to, which is so important to Minnesota, definitely linked into temperatures. This is a rainbow map of our 30-year averages for minimal temperatures. It's cold up here, right? So it stands why you have a boreal system that's occurring in northern Minnesota. And this coldness actually goes westward, of course, through the northern portions of North Dakota. So there's a reason for this. I wanted to go a bit farther. So I acquired climatic information from these data points that you see here, weather stations, because I wanted to link northern Minnesota to parts of Canada to further justify this boreal domain that I'm proposing here. I had some success generating basically two-dimensional graphs in the past. I worked up in Alaska. It worked really well to identify ecosystems at various spatial scales. So I employed that here as well, and this is very simple here. These graphs represent mean monthly temperatures and mean monthly precipitation. And as you see, the numbers of these graphs represent months. So 1 is January, 6 is June, and then it radiates back to 12, which is December. But it forms a real nice package in order to analyze climate, at least at a coarse level. Precipitation is on the bottom axis, temperature is on the side axis. I selected these 3 sites to give you a little idea of a diagonal striking across here. I did these groupings based on the configuration and orientation of these graphs. At the top, we have yellow knife. You can note that the pattern of this is shunted to the left-hand side. So it's a fairly dry area, doesn't receive much precipitation throughout the year, and it's darn cold up there, as you can imagine. The second one is from Ely, and it's indicative of the purple cluster of points here in northern Minnesota. And wow, do you have wild swings of things, don't you, regarding precipitation and temperature? Whoa, you know, really cold territory in the wintertime, radiating to good warmth in the summer and a lot of precipitation before radiating back in the wintertime back in that lower left-hand corner. But look at the spread of data when you're looking at these 2 elements. Pretty impressive. And again, this is indicative of all these sites that are purple, colored purple in this area. And if you look at that inset map, you can see that it goes into different colors, into blues, and we do have 1 green. Those are a little bit different. They have similar signatures, but the difference is in this area, you have 3 months of the year where you have average temperatures that are -10 or lower. So again, it just is a way of basically drawing a line around this boreal forest that occurs. To the east, where you get into the blue dots, this is where you start getting into your classic conifer northern hardwoods, more sugar maple, hemlock starts picking up things like that. So it makes a lot of sense. And you can also see the blue dots right along Lake Superior, right? That's your maritime climate. It all fits together really nicely. Just lastly, Pittsburgh, another representation. This is kind of from the warmer tier points that I had here. You can see where that graph is shunted to the right-hand side in the upper right-hand corner, indicating a lot of precipitation there throughout the year, and of course, warmer temperatures as you would expect. Now, lastly, again, the whole purpose of this was tying climate of northern Minnesota to someplace in Canada. And I was having the dickens of the time doing that, kept on throwing my net out, gathering more data for more points. And eventually I nailed this little community here, Saguenay. It's located north of Quebec City. It had the same signature of northern Minnesota, so bingo, we nailed it. So I think we're in really good straits here of saying that truly a boreal domain exists in this area. Okay, divisions, one step down. And I have included some photos here just to give you an idea of the type of vegetation we're dealing at this level. Note the codification here. So the second column of numbers is what we're using for the identification of divisions. So we have our good old boreal forest that we just talked about so thoroughly. Conifer northern hardwoods represented by the 210s radiating from the eastern portion of Minnesota across Wisconsin, UP, into upper New England. And again, this is your classic conifer northern hardwood forest with sugar maple, red maple, hemlock, cedars, pines, intermix of those species. Good old central hardwoods dominated by and large by oak. There it is. We also have beech maple systems that are integrated in here as well. In the Southlands, we have the mixed southern pines represented by the 230s. Fire formerly was very important there and still is today. It seems like Southerners are very much more accepting of fire than we are. And lastly, 250s, basically representing our tall grass prairie intermixed with oak savannas and woodlands historically. And look at this. This is simply fantastic, isn't it? The state of Minnesota, literally the crossroads of ecosystems. And think about it, this is the highest level of ecosystems that we're breaking out basically, or the second highest anyway. Pretty impressive, isn't it? My goodness, you have boreal forests, you have conifer northern hardwoods sweeping in from the north and east. From the southeast, you have oak-dominated systems very representative of the central hardwoods. And of course, on the western sectors, you have tall grass prairies formerly. Actually, you have one additional one that I just ran out of room. We have boreal parklands that are tucked in there. So there you go. But isn't that simply fascinating? The number of ecosystems at this coarse level that are coming together in Minnesota. Wow, there's nothing like it. And I could share tons of different backgrounds for you as we step through the hierarchy. I just don't have enough time. So basically, I'm just selecting one environmental factor per level. That's all we have time for. And in regards to the tallgrass prairie, this is a productivity index developed from soil properties. And I just want to concentrate on that tallgrass prairie. Look at what it's encompassing there. The greens are representative of very highly productivity soils, highly productive soils, excuse me, the greens. And look at how that eastern line matches so well based on soil productivity. And this is the type of information that we're constantly bringing in as we're classifying ecosystems. So I think we nailed it pretty well. And again, these soils, what are they? They develop under tallgrass prairies. They're mollisols. They're the most productive soils in the world, right? Deep A horizons, a lot of organics affiliated with that. And that comes out very well with this productivity index. Okay, down to the province level. The system that I'm conveying to you was developed by Robert Bailey, and unfortunately he passed not too long ago. But one of the things that he brought into the hierarchy was this M prefix at the province level. This is our third level now. And that is a designation, this prefix, that would drive me wild when I was dealing with databases and Excel spreadsheets and whatnot. Because again, all at once this M would be plunked into this codification at this level. And it made it very difficult when you're trying to, again, work with databases. And we all know that mountainous areas are special. We know that vegetation zonation takes place there, right? But do we actually have to throw it into the codification? I say not, because it's just screwing things up. So I've removed it, And we'll bring this forth through our Washington office leaders to see if they're okay with me removing the sacred M. But believe me, it works so well with it removed. And again, based on the codification here, the first column domain, second column divisions, third columns provinces, you have that linkages interbedded right there. We don't need to screw things up. Okay, so here they are, the provinces, and now I want to actually put a lecture within a lecture, because at the province level and the two later ecological units, sections and subsections, they're very much predicated on the type of surfaces that were laid down 15,000 years ago, at least in glaciated country. The map that you see here, by and large, the greens and the yellows and the deep oranges, that represents deposits laid down by the Wisconsin glaciation. The pinks that you see in Illinois, these were laid down during the Illinoisan glaciation. This is 100 to 200,000 years ago, roughly. And the oranges that you see in the lower left-hand corner, this is pre-Illinoisan. So we have ages, different ages of glacial materials that have been laid down, and then the different colors within that represents different types of materials representing different processes, which we'll go through right now. So the glacial deposits truly sets the ecological stage here by which vegetation dances upon here in the North Woods. So just digging into this subject a little bit, glaciations, surficial deposits. Maximum Wisconsin glaciation took place roughly about 15,000 years ago. Then it started retreating thereafter. And right off the bat, you can see that we have two profoundly different surfaces, don't we? Where the glacier did not pass over, you have these old unglaciated surfaces. Oftentimes altisol soils occur there. They have low base cation capacity there, highly weathered. The soils themselves reflect the underlying bedrock. Oftentimes they had their genesis based on the underlying bedrock. And you can contrast that with all these youthful materials that have been ground up, churned up, and left behind where glaciation took place. Upon retraction, at least in depressional areas, you had vast amounts of water that was ushering forth from these glaciers. And again, in those depressions, you had proglacial lakes that developed. The water that was being emitted from glaciers contained a lot of fine sediments, so silts and clays. The water oftentimes takes on a milky appearance. It's referred to as glacial flour. I don't know if any of you have heard that term before. I got the chance to see it actually up in Alaska. It's really quite cool. But anyway, water's emanating from glaciers, loaded with these fine sediments, being pushed out into these proglacial lakes. In these stagnant water bodies, these fine elements would flocculate, precipitate, and build up on that lake floor. As glaciers would pull back further, all at once you might find yourself where you have terrestrial land now that's in front of that glacier, and just a network of high energy streams that were cascading across that area. These were dumping coarse elements, right? Coarse sediments. So right in front of the glacier itself, you'd have large boulders, rocks, and pebbles being dumped. Farther down, you'd get into gravels. Further from the glacier front, you'd have coarse sands and eventually radiating to the fine sands. And that sequence would set up as that glacier front was backing away from the landscape. It must have been pretty profound. Also, there was so much sediments, coarse sediments that were being dumped on these surfaces that the river systems were very unstable, right? They were constantly building up with these coarse sediments. And as they did so, they would spill over to the nearby depression, make their runs there, load up the beds, and cascade back into maybe their original position. And that's why you have all those interbedded surfaces if you do look at cut banks or go to sand or gravel pits. Really super interesting, a very dynamic environment at that time. Lastly, where you have ice that just melted out basically in place, you end up with these morainal tills. They're referred to very hummocky areas oftentimes. Some of these ice chunks were left behind up to 4,000 to 5,000 years before melting out. So think about the storyline I just delivered and what's there now. Where we had glacial lacustrine deposits, poorly drained, laden with clays. And that very dynamic surface laid down by rivers and streams, we have now excessively drained glacial fluvial outwash plains, right? Sands and gravels. And lastly, up on the right, over to the right-hand side, we have well-drained ice contact materials. Oftentimes these are loams. These are unsorted materials that were represent everything from erratic boulders down to sand silts and clays mixed together. Now, let's think about the vegetation. Let's do a cross-section, let's say from Kentucky northward through Ohio. Old unglaciated surfaces, alto-sol soils, here oak hickory country, right? Where you have these poorly drained glacial lacustrine deposits. These are very wet areas, obviously. And because they retain water so well, you have marshes and swamps. Historically, elm ash. Ironically enough, Dutch elm disease wiped out the elm wood back in the 70s and 80s. Now we're dealing with emerald ash more. Where's the system going to, Lord only knows. Glacial outwash sands, they tend to be fairly infertile, tend to be very dry. Here's your classic pinery, right? Eastern white pine, red pine, jack pine. Those three species set up along a edapho moisture gradient. Eastern white pine occurring on the finer texture soils, the better soils. Red pine less so, and on the most infertile and coarse textured soils, we have jack pine, of course. And this is the place where, of course, fire was king, right? These are drier landscapes, and you had vegetation that was very conducive to burning. Lastly, well-drained ice contact morainal tills. These surfaces, again, tend to be loams, unsorted, all churned up, very fertile. And this is where your classic conifer northern hardwoods oftentimes can be found. Now, watersheds are always brought up as an ecological unit, and it's indeed very important for a hydrologist and fish biologist, right? It's a gravimetric unit, but you don't want to necessarily equate that to what is being presented here, terrestrial ecological units. If we were to superimpose a watershed, this gravimetric unit over this area, look at all the different ecosystems that are being encompassed within this watershed. It just doesn't do it justice, if you will, looking at these things from a watershed perspective. Just think how water quality and quantity changes as you go from the morainal tills across the sand plains into clay basins and ending up in an unglaciated territory. That water quality and quantity is changing profoundly, isn't it? And it's changing profoundly from one surface to another. So watersheds, again, important for fish biologists, aquatic organism passages, understanding that. And I think there's a big benefit to superimpose the two together because watershed people can gain so much by integrating these ecological units into their field of study. Okay, that's enough with our glaciation study, and back to the hierarchy here. This is representing sections at this time, concentrating on the upper Midwest. Note that at the end of this alphanumeric code, we have a capital letter that is identifying sections that are occurring here. And again, this codification that I'm showing here is really neat because then you can understand where you are placed within this ecological hierarchy. It's quite powerful. Again, I'm limiting myself to just one environmental factor per layer, and this one I chose soil texture surface, sands represented by reds, silts, greens, and blues representing clay. And look how nicely those lines tuck in to these different surfaces. And again, this is reflective of what past glaciation and how those deposits were left on the landscape. Pretty cool. Here we have Glacial Lake, you can see it up there, sticking its nose down, represented by the blue clays. And the last ecological level that I'll present here today are ecological subsections, and they're denoted by a small letter at the end of this code. You know it quite well. Drainage index was selected for this one. You can see again how these lines capture different drainages, going from excessively drained with the hot colors to poorly drained in the cool blue colors. And again, Glacial Lake, you can see it shows up very nicely here, and you can see how we captured that with these delineations at this level. And since this is a fire conference, surely I should have one slide pertaining to fire. This is something I presented not too long ago, I think at this very conference. Working with Melissa Thomas Van Gundy in the witness tree database that John Almendinger put together. We categorize trees simply into two units, pyrophilic and pyrophobic in nature. So pyrophiles would be oak and pine, for instance, pyrophobic species, maple, elms, hemlocks, things such as that. Binary system, very simple, right? But at each witness tree point, you can have 2 up to 4 trees that occur. So we could calculate, if you will, a pyrophilic percentage at each point. So if you had 4 trees and they were all pyrophilic in nature, you'd have a score of 100. If they're all pyrophobes, 0, and different percentages based on the intermix of those 2 groups. That gave us a point database, and that point database then was created, producing this surface that you see behind me. And I just wanted to bring this one up as well because, one, we use this information to improve our subsection lines, working with John and Dan and others, and you can see that reflected here. So this is kind of a new element that we brought in and trying to bring in disturbance regimes, past disturbance regimes into our classification, because you know how important fire is on the landscape historically. The reds represent areas of high pyrophilic percentage. The greens are where you have a low pyrophilic percentage. So it just gives you a feel basically of how important fire was in the past landscape. Look at this little sandbox here in northwestern Wisconsin. Many of you are familiar with, right? That just lit up immediately and it's surrounded by a pyrophobic area. Okay, winding down here, John requested some additional time for his presentation, so I think I can deliver. Why ECOMAP Products? Easier decisions. We have ecological defensibility with this product. Gained efficiency through ecological addressing. We can record what management activities work and what don't. And we can transfer those successes into future plans using ecological units. And of course, we want to avoid duplicating mistakes along the way. Land management questions differ spatially and require hierarchical frameworks. And that's what this delivers. We have questions for the U.S. Forest Service that come from the Washington office. We have questions that I have at the regional office. We have questions that occur at the forest and district levels. This hierarchy can accommodate all those questions. And truly, ECOMAP puts the E in ecosystem management. How can you conduct ecosystem management without knowing where your ecosystems are on the landscape? So this is foundational to what we do as land managers. Spatial relationships. What's neat about our hierarchy is that it allows for understanding spatial relations among ecological units. If you want to know more about the spatial context of an ecological unit, all you have to do is go up one scale. For instance, line type association to subsections. Now, if you want to know more about the spatial content or components of an ecological unit, more specific information basically, you go down one scale, and in this case, a land type association to a land type unit. This is really powerful stuff, isn't it, when you think about it? This ability to go up and down the hierarchy. If you need to know where you are, you can do that. If you want to understand more about the components, you can do that as well. So what's your ecological address? And we do know that a boreal system does exist in northern Minnesota now, doesn't it? So with that, thank you for your attention. I hope you enjoyed today's presentation on ecological mapping and classification, and hopefully you can put it to use in the near future in your line of work. With that, Eli, how would you like to handle things? We have 16 minutes left based on your time.
Let's do questions right now. So I've got 3 questions in on the system so far. I will mention, I know I won't name her, but I know there's at least one person in here who doesn't have a cell phone. If you want to, I do have cards here, and I don't know how best to distribute these, but I'll kind of put some around. Pass them down if you don't want to put something online, you can use those. But I really encourage you to Do that. And Jack, are you willing to maybe collect those up and down the aisle? So raise your hand if you got a card or something. I'll send Jack over. So the questions, I should talk into the mic. The questions that we've got so far, Greg, Northeast Minnesota is classified mostly as fire-dependent forest, but the pyrophilic maps that you showed showed a moderate occurrence of pyrophilic forests. What's up with that?
Yeah, I think we have an intermix of fire regimes that are occurring in the northeastern part of Minnesota in the Boundary Waters area. The map that I showed was rather coarse, and we could dive a little bit more specifically into the pyrophilic map, but it shows that. So you have areas that are dominated by jack pine that just light up red. Working with my Superior folks, we've seen that, and we incorporated that into our delineations at finer scales yet. So it was a mixed regime of fires that occurred there historically. Areas that were, for instance, more peaty in nature, more moist, those areas had more subdued fire regimes. So fire wasn't necessarily a big player in some of those areas. Whereas on, again, surfaces that had coarse textures underlying it, those areas that were dominated by pine, surely fire was very important there. So it's just an intermix there of fire regimes and consequently vegetation types.
Great. Next up, is there any boreal intrusion into the Acadian systems of Maine and adjacent Canada?
Yeah, that's a very good question, and I was kind of expecting that to occur. However, when I was accumulating ecological units from Canada, and I'm thinking about the eastern sectors of Quebec and New Brunswick, and started looking at the definitions they were using, there was a lot of hardwood species occurring, particularly in New Brunswick: sugar maple, red maple, northern red oak, and those hardwoods were intermixed with red spruce, for instance. Red spruce, incidentally, is not necessarily a boreal species. It's more of a temperate species affiliated with the Allegheny, or the Appalachian Mountains, excuse me. So based on the surrounding provinces of Canada and the fact that these more warm broadwood leaf species were occurring, I kept it as conifer northern hardwoods. And it's a very good question. Wow, I don't know who posed that one, but man, that's pretty impressive. Wasn't expecting that one to be touched on today.
All right, there are a few other questions there. Is there a temporal component to mapping? Does the classification change with time, and if so, at what rate?
Yeah, that's a very good question. And of course, now we're starting to touch on climate change. We do know that over time, there's been a warming trend taking place in the eastern United States. Precipitation is kind of across the board right now, with increases in some areas and decreases in others. That's kind of a wild card right now. But we have been focusing in on the stage, okay, on those edapho elements, soil properties, again, physiography, topography, to lock these lines into, okay? And we know that over time with climate change, the species are going to be shifting. But what's kind of neat about this is that it allows you to see how vegetation is changing over time as climates change. So basically, this is a point in time that 20 and 30 and 40 years ago, we can go back and see if these changes have taken place using these ecological units. And over time, they might be modified, right? This boreal domain that I showed you, maybe those southern subsections eventually are going to get knocked out and pushed back to humid temperate domain, for instance. Another thing in regards to the climate change, I want to roll on this one a little bit. It's going to spin out very differently based on these ecological units. Just think with the example of the glacial lacustrine clay basins, the glacial fluvial outwash plains, the morainal areas. Just think how climate change is going to affect those ecosystems. It's going to be profoundly different in those surfaces. Wet surfaces are going to still stay wet, right? Glacial fluvial deposits, they're going from maybe being dry today to very, very dry in the future if things really warm up. So again, it provides a nice template because we're locking into these edaphic lines or properties by which we can document how climate change affects the vegetation over time, which will differ based on environmental sites themselves. And again, it's modifiable by which we can always move divisions, domains, provinces, one way or the other, if we're concentrating on vegetation.
Next is an interesting one. Baselines are incredibly important to modeling and perceptions. How might the pyrophilic versus phobic model be different if 1750 or 1950 were the baseline?
Yeah, we can have a whole, I can deliver another presentation on musification. How does that sound? But yeah, baselines, obviously they change over time. The pyrophilic map that I presented was based on witness trees, trees that were surveyed back in the 1800s up to around 1900. We do know that over thousands of years, the disturbance regimes have been changing. In part, they've been changing along with how climate was shifting, going from the hypsothermal, for instance, to now we're in the neoglacial period, although warming within such. So yeah, baselines, it's all about when that information is being derived from. Witness trees are nice in that at least it gives us kind of our best idea of the type of compositions that took place when Europeans came to this landscape. And oftentimes it is used as a baseline. And it does capture well, in that case, pyrophilic percentage, you know, what type of, how important fire was on the landscape, using tree species, their ecophysiologies as a baseline or as an indicator of fire.
We'll do one more and then we'll go to our next speaker. There are a few questions here, 3 questions that relate in one way or another to crosswalks or comparisons between this hierarchical system and the Minnesota DNR's Native Plant Communities hierarchical system. How exactly did DNR Native Plant Communities fit into the ECS hierarchy? Are they land types, land type phases, or something else?
The next speaker can answer that.
All right. I'll leave those questions up. All right, Greg, thank you very much. Great. Really good start to the day here. We're going to go next to John Almendinger. John is well known to this room, I suspect, certainly to many of us here. John is recently retired, still youthful and spry, but doing new things, and we're glad to have him back. John, let me see if I can figure out how to